Welcome to the Earth Science Classroom. We're looking at geomorphology and Earth as a system playlist. Looking at lag time today, and lag time in this video we'll look at a few things. We'll look at what it is and why do we look at this, why do we focus on lag time in a system, and how it applies to geosciences and how we kind of interpret this in terms of the processes that occur on the landscape. We're going to look at the classic examples, look at the terminology, the terms, and the different characteristics of lag time. We're going to look at the graph because obviously it's a great way to show and illustrate what is going on in terms of changes to a landscape. So the graph is used to visualize that. And then we're going to look at how it connects up to things like equilibrium, EQ, the different spheres, also how we study geomorphology as an intro to this unit. All right, so let's look at what it is. Okay, so let's just look at the lag. Lag is something that happens behind or after. So there's a time difference or time delay. It's going to happen after the fact. So something happens, so there's an input, there is a time duration, and there's an output. There is a cause, and then there is an effect. And the effect could happen after the fact. It could be a different time, but in relation to what's going to happen, it's going to happen after the fact, and there'll be some sort of like downtime, some slow reaction curve in the system to create the effect. So what this really looks at is a definition: the time required for a landscape to change in response to changing conditions. So obviously change is a major part. Obviously we've got there the time required, so a certain duration, and there's going to be a resultant change to the conditions. Okay, so a lag time is very important to appreciate because it is an essential part of the Earth system in a way that something happens, the Earth system, let's say it's the hydrosphere or the atmosphere or the biosphere, there'll be some time whereby the change is taking place. There is some sort of reaction in the landscape or on the landscape to the change, to the disturbance, and then the outcome will happen after a certain time. So we're discussing the effect in terms of the spheres and in terms of the interactions and in terms of nature and the processes that govern nature and the inputs and outputs, and in terms of systems as well. So this is all involved with systems and how lag time works within a system, to control a system, to dictate a system, to even change the system. And this can go back to and link up to equilibrium. Because the lag time could be the time it takes for a system to resort back to equilibrium or dynamic equilibrium or even steady state, or even it could be a long time. There could be positive feedback loops in play that could cause a very long lag time to occur, or there could be some sort of metastable and changes with the threshold, which can also impact the lag time and how long it takes for a landscape to change and respond to the conditions placed upon it. For example, look at nature. So in nature, we've got the classic one, let's say flooding. So with flooding, looking at the hydrosphere, Looking at the geosphere, obviously happening on top of the Earth, on the Earth's surface. We're looking at the lithosphere in general, or toposphere in general, and it can even involve the biosphere, and of course the flooding originates from the atmosphere, so we can put that in there as well. And you can even involve the cryosphere if looking at spring melt or any kind of lahar or a volcano that's melting the ice. So you could definitely involve all 5 spheres if you want. Now, flooding is something that's based on the fluvial system and the location and the topography and gradient and slope, that it could rain in a certain area, it could produce overland flow through the catchment area, through the watershed, through the different order of rivers and streams and brooks, and cause an immense amount of large discharge to come out of the river system or down the river system. But it would take some time from when it starts to rain heavily to the accumulation of water through the watershed to eventually create that large discharge and that large rise of the riverbanks and flooding and velocity change through the actual river. It takes time to happen. Maybe 1-2 hours, depends on the environment, depends on the slope and gradient and a lot of other factors. But flooding is that classic example of that kind of that short lag time. There's a lag time, let's say in hours, but it's short. Now, to longer lag times, maybe looking at orogeny and mountain building. A coastal mountain range starts to develop over the course of millions of years, and that would eventually change weather patterns, elevation, climate, terrain, vegetation, ecosystems, you name it. There's a long change over millions of years. That could also be lag time. Now, in terms of what causes the change to happen or the lag time to happen, is called a disturbance, all right, or perturbation. Disturbance is a change that affects the landscape. That change is a very fluid term. So disturbance comes in 2 types. There is persistent or semi-persistent or semi-persistent. There's also discrete. Discrete is one time only, is a single event. So discrete, I would look at maybe a meteorite impact, the crater, okay? Maybe it's the KT extinction event 65 million years ago that the dinosaurs said goodbye to, or most of them said goodbye to, on that lovely, ominous day. Or something persistent, could be climate patterns, could be seasonal rain, monsoon season. It could be forest fires every season, like in the western United States right now, in Northern California, Oregon, in that area. It's extremely dry and having that very large drought in the southwest and forest fires and all that horrible, unfortunate stuff that goes on with that part of the world in terms of natural disasters. So the 2 types of disturbance is going to have a great effect on the environment, and the lag time is going to be between that disturbance to the actual outcome or the changed landscape. All right, so this is the graph part. So I like using graphs because it is an essential skill tool to utilize in the classroom to explain phenomena, to explain processes, relationships, direct and indirect proportion, and how things change over time, or just to add in that math component, because at the higher levels of geoscience and earth science and physical geography, you're going to add in a lot more math or mathematics in order to explain these processes and explain the changes that happen through math equations, formulas, and obviously graphs. And graph can tell you a lot than just writing out in words. So I have my energy input landscape change here on my y-axis, and on my x-axis, I have my time. So let's just say the environment is at, say at to either do dynamic equilibrium, you'll even use the term steady state, you can even use the term stable if it is, it's very hard to find stable, but could be stable. But you have this environment where over time it's not changing. You see on this energy input on the left-hand side axis, the y-axis, there's no change. So it's very, very stable. It could be a climax community in a forest. It could be an ocean. It could be a raised landscape, whatever. Then what's going to happen is, use this green line right here. We're going to have a disturbance, a forest fire, a landslide, an earthquake, a volcano, a monsoon, the wet season. It could be as simple as a rock slide, or it could be as devastating as a meteorite and changing world climate, or a massive, huge VEI 9 or 10 eruption from a new Krakatoa or Yellowstone National Park caldera. But disturbance, it's going to be a change. A change will occur, but over time. Now, this landscape, okay, let's just say it's a forest fire. So you got a forest. It's going to change. The trees are going to burn. The forest fire will go as fast as the wind speed will take it and the conditions, and it's going to change the landscape. What you have is this forest is going to change, and then there'll be a new equilibrium. So this could be unstable, it could be metastable. And the disturbance is going to happen, and over time, from here to here, okay, let's just put another, let's do a purple one. There we are. So this time, from here to here, is called the response time. How long it takes for the landscape to respond to the forest fire, to the trees burning, to the ash, and the level of succession that's going to happen in that forest. So the time it takes to respond for the landscape after this forest fire is including two subcomponents. Okay, there's one here and there's one here. This first one is called the reaction time. Okay, the time it takes for a landscape to react to what has happened. So with a forest fire, you might get a very, very small or short duration reaction time, because if the conditions are right for the forest to ignite and combust and flow through with a high wind, it can be very, very short time and also very devastating. But let's say if it's a large rainstorm over Arizona, dry, arid conditions, then you might have a longer lag time, a longer reaction time for the flood to come down the river. So it depends on location, that can change. The next one is called the relaxation time. Now, it's a strange word to use in this context because you think that this environment is not relaxed, it is changing, it is under stress, different energy inputs. Forest fire is not relaxing in any, but it's in terms of relaxation means like it's going to adjust. How and how long the adjustment takes for the location or that location. So it's adjustment. So reaction and relaxation are all part of the response time. And the response time goes from the second the disturbance happens to when the conditions come back to a new equilibrium. Maybe this never comes back, or maybe this will come back down, and it'll be some sort of negative feedback loop between. It also depends on the time. You look at the time in terms of days or weeks or months or even decades. You'd see that natural course of succession through ecology, and you see that it's a negative feedback loop where you have a disturbance, a change, the response time, a new equilibrium, and then the forest and tree is going to grow back through the burnt ash and timber, creates more nutrients to the soil, and then it's going to reignite the growth of a new forest. Old growth versus new growth. So again, we can also discuss the term cyclic in terms of time, and we can also discuss equilibrium, states, and also the patterns of nature. So we also have to understand that there are different thresholds. So there's a threshold here going through the regular equilibrium, and there's also a threshold up here, the top. And these thresholds show or illuminate or tell us the boundary between the states, boundary between each of the systems. The system has a barrier, a boundary that it's going to create its equilibrium within. And once that threshold is been surpassed or broken or destroyed by that disturbance, then there's going to be, obviously after the response time, there's going to be a new threshold which will be created with that landscape because of the disturbance, a brand new threshold, so a new level of which the system can work with, some different parameters, or even a new equilibrium. Now, within systems and lag times, there are 3 R's we have to consider when looking at a certain environment, landscape, terrain, and the effect of a disturbance and the kind of disturbance that happens on that exact location. So, first one is resistance. Resistance is obviously the ability for a landscape or condition to avoid or lessen the impact. So it's how resistant is it? So, example, the Northwest states, Oregon, Washington, Northern California. Right now, the whole area is very dry. It had a recent heat wave, and the forest is very dry, and the ability to resist any kind of forest fire is severely decreased due to the climate and environmental conditions currently there. So the resistance in that sense will be very, very low. Whereas let's say a forest fire in an urbanized area where the tree in the northeast of America, where there's lots of rain and everything is hydrated and the water table is very high, the trees have lots of moisture and water to use, then that will be a very diminished or higher resistance to the forest fire. So that's the first one, resistance, very important to look at. Next is resilience. Something is resilient, they are going to battle against something. They're going to be strong. And in this case, it is the ability to recover. So it's in relation to the response time and how efficient is the environment to respond and react through its response time to that disturbance and to get back on track in terms of creating a new threshold, new equilibrium, or even a negative feedback loop. So resilience is also a very important part of a system, especially with geomorphology and how it reacts, how it recovers, the speed of recovery. Then you've got recursion. Recursion is to do with feedback loops. Is it going to be a negative or positive? So If it's positive feedback loop, that environment will not go back to its original state or its previous equilibrium. It will just keep going and change and change and change. For example, let's say like the KT extinction, that crater, that meteorite hit the Yucatan Peninsula, and the world was changed for a long, long time. Then a negative feedback loop is there is a disturbance, a change, and there is a consistent pathway back to original steady state or dynamic equilibrium that was prior. So it's a small fluctuation that causes a time in which the environment is going to go back to its original state, like a flash flood, for example, in the southwest of America. So recursion can also we can also link that up to equilibrium, and it's obviously depend on the landscape and particular area you're looking at. And the main rule to remember is that the larger the disturbance is going to create a longer lag time for that landscape to recover. Again, from small disturbance to large disturbance, you can imagine that the reaction in both the response time, the relaxation time, reaction time, and the 3 R's: resistance, resilience, and recursion. And as a summary, in terms of the cyclic or cycles of these lag times and disturbances, you've got the independent versus dependent. The independent is going to be the cause. So we've got cause right here. But independent, and dependent is the effect. And in regards to cause and effect, looking at the time dependent. So looking at the different stages. So this will be in stages of lag time, the stages of rebuilding through that lag time, through that relaxation time to a new threshold, a new equilibrium, a new landscape. So time is important because it takes time to go through each stage. Or you have a situation where there's time independent, where time doesn't really matter because it's usually going to be an open system and inputs change with time. Therefore, there is no guaranteed or definitive stages that it goes through. It's just an evolving landscape that time really doesn't have much importance. You can't really use time as a gauge because it's constantly changing. So we put constantly changing. All right, guys, hopefully you enjoyed this video. Check out this more playlist videos on geomorphology and other systems. If you didn't subscribe and like the video, please do so. It's always great to have people liking the videos.